Hello and welcome. Today, we're diving into the fascinating world of 3D bioprinting, a technology set to reshape regenerative medicine. Imagine printing replacement tissues or even organs layer by layer. That's the promise of 3D bioprinting. It uses biomaterials, living cells, and growth factors, collectively called bioinks, to create intricate structures that mimic our own bodies. A key element in this process is the engineered scaffold. Think of it as temporary scaffolding for buildings, but on a microscopic biological scale. These structures support cells, giving them a place to attach, grow, and organize into functional tissue. Ideally, these scaffolds are biocompatible, meaning friendly to the body, and biodegradable, dissolving away as new tissue forms. They also need the right porosity and strength for the specific tissue being repaired. 3D bioprinting allows incredible precision, often using patient-specific data from CT or MRI scans to design these scaffolds. There are several ways to print. Extrusion-based printing is common, pushing bioink through a nozzle, good for dense cell populations, but sometimes tricky for cell survival due to pressure. Inkjet printing deposits tiny droplets, which is gentler on cells but usually requires less viscous bioinks. Light-based methods, like stereolithography, use light to solidify photosensitive bioinks, offering high resolution but needing specific material properties. Then there's laser-assisted bioprinting, which uses lasers to propel droplets, minimizing stress on the cells and achieving high precision. The choice of bioink is critical. It needs to be printable, yet support life. Natural polymers like collagen, gelatin, and alginate are popular because they resemble the natural cellular environment. Decellularized matrix, essentially the scaffold left after removing cells from tissue, is also very promising. Synthetic polymers like PCl or PEG offer controllable properties. Ceramics like hydroxyapatite are great for bone. Often, materials are combined into composites to get the best of all worlds: printability, strength, and bioactivity. How do cells get incorporated? Sometimes they're added after the scaffold is printed, a process called cell seeding. Other times, cells are mixed directly into the bioink before printing, allowing precise placement within the structure. So what's being achieved? Researchers are making strides in printing scaffolds for bone and cartilage repair. Layered skin substitutes are being developed for wound healing. Progress is being made in cardiovascular tissues like blood vessels and heart patches, although making them fully functional with blood supply remains a challenge. Scaffolds for nerve regeneration are being explored. And significantly, bioprinted organ models like mini livers or tumors called organoids are becoming valuable tools for testing drugs and understanding diseases, reducing the need for animal testing. Despite the excitement, challenges remain. Getting blood vessels, vascularization into larger printed tissues is a major hurdle. Cells need oxygen and nutrients to survive deep inside a construct. Ensuring cells stay alive and functional long-term, matching the mechanical strength of native tissues, and scaling up production for widespread clinical use are also key issues. Developing reliable, standardized bioinks and navigating regulatory approval are also critical steps. Looking ahead, the future is bright. We're seeing trends towards printing with multiple materials simultaneously to create more complex tissues. Smart bioinks that can respond to body signals are being developed. Artificial intelligence is helping optimize designs and printing processes. And there's even 4D bioprinting, where printed structures can change shape or function over time after implantation. Combined with engineered scaffolds, 3D bioprinting truly holds revolutionary potential for personalized medicine, tissue repair, and, maybe one day, ending the organ transplant waiting list.